This is the problem on ultrasonic heating, which says deep ultrasonic heating is used to promote healing of torn tendons. It is produced by applying ultrasonic sound to the body. The sound transducer generates a circular with a radius of 1.8 centimeters. So it says, okay, we have R equals 1.8 centimeters. Probably at some point you need to convert that to 0.018 meters. And it produces a sound intensity of 5.9 10 to the third watts per square meter, so 5,900 watts per square meter. And it says the sound intensity, and we can look that up here in this chapter. It's given as I equals P over A, power over area, and that makes sense. Look at the units, watts divided by square meters. Oops, and there's supposed to be an equal sign. And then it says how much time is required for the transducer to emit 4,800 joules of energy. So it sends out a certain amount of radiation energy. In this case, I just call it capital E for energy. So 4,800 joules, and then the unknown is T. Let's just have a quick look here at how a transducer looks like. I googled that and I came up with this particular company. I think you can see the link there that is selling it, and I guess here you have this transducer, the ultrasonic one, and it sends a sound wave in there and that heats the tendon and therefore it heals it. I'm not a medical doctor, so I wouldn't actually know how it does that, but in any case you get somewhere here, should be the unit right somewhere in here, that sends the sound wave in, probably to a pretty local area, so that only that particular area, the tendon in this case, is getting heated. Okay. In any case, in order to do the problem, so this is what we have to figure out, time t. Look at the equations that are given so far, and there really is no time given, so we have to see how we get there. Again, this problem also has a star, which means that it's either harder or go back to a previous chapter, figure something out, or both of those. In this case, go back to a different chapter and notice that the power P that is kind of inside here is given as P equals energy divided by time. You find that in the chapter on energy that lists the power law towards the end of it. Okay, so E over T, and then of course here's the T right there. The A here, well, it says it's a circular area, so it would mean that with a circular area we have pi r squared. That's how it's radiating. So that transducer, I guess, is circular. And then I take these here and I plug these in these two equations, and I'm going to come up with that the intensity P over A equals E over T. I think I'm gonna write it with a horizontal fraction bar, so E over T divided by pi r squared, and then it's a matter of doing the algebra, and that comes out to, let's see, T equals E over pi r squared, and also divide by I, capital I for the intensity, with everything given. You know, here's the 4,800 joules, here's the 5,900 watts per square meter, pi, and of course the R is 0.018 meters, and then you're going to come up with something, and at this point everything is given in base units, so it will come out with the standard or base unit for time, which will be seconds. On a side note, I figured out, or I looked into, well, what would happen if, or I looked into, well, there's a certain amount of energy going in there, which means it's gonna heat up. So I figured, oh, I'm curious about by how much actually would it heat up. And so here's basically what I did. First of all, I looked at a tendon. So I would have the transducer sitting out here, and it's going to send a sound wave in, and it has this radius of 1.8 centimeters, which means a diameter of 3.6 or about an inch and a half. And then it's going to have a certain depth, so it's going to heat a certain amount here. And I figured, okay, the amount that I have there is roughly 50 cubic centimeters, 5 centimeters deep. I just made that assumption, 5 centimeters, 2 inches deep. Come up with roughly 50 cubic centimeters that it heats up, which is also about 50 grams, taken that the human average density is about 1.0, same as water, very similar to water. And so I come up with like 50 grams, and then I figure, well, it's probably going to have a heat capacity in the neighborhood of that of water, so roughly 4,000 joules per kilograms and kelvins, and then it puts in a certain amount of energy, 4,800 joules. Okay, and then times this one here, which means at this point I should take this away, and respectively that I should actually write not 50 grams. And of course, what I'm doing here is on top of the problem. I should write 0.05 kilograms here times a certain increase in temperature. And when I do that, I come up with an increase of temperature of 24 Celsius degrees when you put 4,800 joules into this small area. And that seems a little bit dangerous. That's kind of in the neighborhood of 40 degrees Fahrenheit, so it would heat up to 130 Fahrenheit. It's like, no, that can't be. But the thing is, the clue is in the time that you're going to come up with, that is spread out over time. So the increase per second is actually rather small. You'll see you come up with a relatively large number for the time. So each second the increase in temperature is a little bit, so it heats it up, but over time it also cools because there's tissue around it, which then will absorb that excess heat. So I'm sure it's not going to heat up to 130 Fahrenheit, but just perhaps by a few degrees, maybe. I'm just guessing 110 degrees or something as it cools all the time. Anyway. So again, this was on top of the problem. The problem was already done earlier when I was done here with the algebra.